Hello everyone, my name is Frederick Riemenschneider, and together with Kevin Krahn, I participated in the SIGTYP 2024 shared task on word embedding evaluation for ancient and historical languages. Current research on word embedding evaluation focuses almost exclusively on modern languages, such as the XGLUE or the Extreme task. For historical languages, on the other hand, there is no such widely adopted universal benchmark. The SIGTYP 2024 shared task can be seen as one step in creating this benchmark to evaluate embeddings for historical and ancient languages. It covers 16 languages that belong to 4 different families and use 6 different scripts, for example Ancient Greek, Ancient Hebrew, Classical Chinese or Coptic. It consists of 2 subtasks, namely an unconstrained and the constrained setting. In the unconstrained setting, basically everything is possible and allowed. That is, one can gather pre-training data for specific languages or train multilingual models and utilize the ability of language models to generalize across languages. In the constrained setting, only the fine-tuning data provided by the task organizers is allowed as training data. Even pre-trained language models that are traditionally used, such as XLMR, are not allowed. We participated in this more restricted constraint subtask, where only the task data is available to us. In the constraint subtask, there are 3 problems we have to tackle: word-of-speech tagging, morphological tagging, that is, a complete morphological analysis, and lemmatization. Our research question is, how can we extract as much information as possible from the provided data? This is particularly important for historical languages, as their closed corpora usually lead to low resource scenarios. One important component of a language model is its tokenizer. As we are ultimately interested in word-level representations, this would be a natural choice. But we are in a low resource setting, and thus many words would never be seen, or only once. Further, historical languages tend to be morphologically richer than modern languages, which exacerbates the problem. A very common choice is to use subword embeddings, having a trade-off between word and character level tokenization. However, we still lose much information as the model perceives combinations of characters as one token, and the characters a subword consists of are completely opaque to the model. Moreover, we don't have explicit word representations as words are split up into multiple tokens. Finally, there's character level tokenization, of which we hypothesize that this is the tokenization method that gives the most meaningful information to the model. The model can learn from every single character. However, this results in extremely long sequence lengths, which is a problem due to the quadratic complexity of the attention mechanism. And still, we don't have explicit word representations. As a solution, we adopt a hierarchical approach proposed by Lisanne and colleagues in 2023. Here, the tokenization works as follows. Every word is represented as a special word representation token and the characters it consists of. First, a relatively shallow transformer called intra-word encoder is provided with this input. This intra-word encoder now produces embeddings that are contextualized by the surrounding characters of a word. Now we have a special word representation token that is informed by all the characters the word consists of, and we have characters that are also contextualized by the surrounding characters of a word. Now we use a deeper transformer called inter-word encoder to get word representations that are contextualized by the surrounding words. So this is basically the equivalent of a quote-unquote normal transformer. During pre-training, we employ one last shallow transformer that is called intra-word prediction head. This prediction head uses the contextualized word representations and the character representations outputted by the intra-word encoder to perform the pre-training task. In this figure, it's masked language modeling. So this is the hierarchical architecture that we use. We highlight that with this approach, we have the advantage of an open vocabulary. As the underlying language model, we use the Bertha version 3, which is, to our knowledge, the most advanced encoder-only language model, implementing several architectural benefits such as gradient disentangled embedding sharing. As the pre-training objective, we use replace token detection, which was introduced in the Electra paper by Kevin Clark and colleagues. One language model, called the generator, is tasked to do masked language modeling. Now we have a sequence where the masked parts are predicted by the generator. This sequence, which contains the predictions of the generator, is fed to a second language model called discriminator. In our figure, most of the characters were correctly predicted by the model, but one token, marked red, was incorrectly predicted. The task of the discriminator is now, for every single character, to decide whether the character is coming from the original sentence or whether it was produced by the generator. In our case, where the generator achieved almost perfect performance, the discriminator has to identify the token O, here marked in red, as a token produced by the generator. It has been shown that this pre-training objective is more effective than traditional masked language modeling. For downstream tasks, we disregard the generator and utilize only the discriminator. We experiment with the following masking strategies for the generator: whole word masking, character masking, and character engram masking. In whole word masking, we randomly select 15% of the words and mask all the characters in them. In character masking, we randomly select 15% of the characters and mask them. And finally, in character engram masking, we mask random spans of 1 to 4 characters until 15% of the characters are masked. We found that character engram masking worked best for our model by a small margin. We hypothesize that it is too difficult for the model to learn to predict whole words, and that it is too easy to predict single characters. This hypothesis is supported by the fact that masked language modeling performance of the generator reaches very high levels very quickly. What we described up to now is our hierarchical deburter version 3 model. Such an encoder-only model is appropriate for sequence tagging tasks, such as part-of-speech and morphological tagging. The third part of the SIGTYP constraint subtask is, however, lemmatization. While there are many approaches considering lemmatization a classification problem as well, we think that it is more naturally treated as a sequence-to-sequence task. Unfortunately, there is no straightforward way to extend the hierarchical model to decoder-only or encoder-decoder models. Therefore, we train character-based T5 models for lemmatization. Now, we have described the hierarchical deburter version 3 model for part-of-speech and morphological tagging and the T5 model for lemmatization. We pre-train these models on the training data provided by the task organizers, meaning for each language we pre-train a hierarchical deburter and a lemmatization model. As the training datasets are very small, pre-training can be done very quickly. For example, training a T5 model for 100 epochs on the largest available dataset takes approximately 3.5 hours. So let's see how our models perform. These are the results for morphological tagging. The systems coming from the unconstrained tasks, namely UD, parse, and Tatu-NLP, are colored red, whereas the systems we are comparable to, that is, the systems from the constrained subtask, are colored blue. Looking at the constraint setting, our system emerges as the clear winner, being superior in all languages. Even when looking at the unconstrained systems, our model is highly competitive and can even outperform the unconstrained task winner in ancient Hebrew. In general, however, our system falls minimally behind the unconstrained tasks winner. This trend also holds for part-of-speech tagging, where our system again emerges as the winner of the constrained task, while often almost matching the performance of the unconstrained subtask. Results are a bit more diverse in lemmatization. In most languages, our system outperforms other approaches in the constrained subtask, but the systems seem to have different strengths in the lemmatization task, likely due to different architectures. This is similarly true for the systems of the unconstrained task, resulting in our system outperforming the unconstrained task's best system occasionally, while being clearly outperformed in Sanskrit. A more detailed analysis of the results can be found in our paper. What we presented so far was the system we ultimately used for the shared task. We experimented, however, much more, especially with multitask learning. For example, we tried to add dependency parsing as an additional task, believing that the additional training signals could improve performance for the tasks of interest. However, we observed that the models converged much more slowly while not improving the part-of-speech or morphological tagging performance. Moreover, we experimented with taller models, meaning that we tried out a narrower and deeper architecture. Previous work found that this architectural change often results in superior performance. However, while we observed slight improvements when training with masked language modeling, we did not see benefits when training with the replaced token detection pre-training objective. To conclude, we implemented a hierarchical language model to learn efficiently from every single character. We used deburter version 3 with replaced token detection and treated lemmatization as a character-level sequence-to-sequence problem. Our results were promising, winning the constrained subtask of the SIGTYP 2024 shared task while being highly competitive with the winner of the unconstrained subtask. For more details, check out our paper. Thank you for for your attention.